good evening, audience in the United States, and good morning to local NTU graduate students. The joint seminar webinar series 2025 is jointly held by the CDA of UIUC, CIA of NTU, and the Department of Biometronics Engineering, National Taiwan University. Today is the second of the series, Controlled Environment Agriculture. And we will have the third in the April and the fourth in the end of the April. The two will cover smart agriculture in animals and crops, which are recently very significant topics. So please make notes on your calendar. So today we will have 4 speakers, and Professor Fang, Professor Ting, and myself, and Professor Davidson. So since we have a very talent and knowledgeable speaker, so I try to keep the introduction short. So Professor Fang, can you start to present, to have your presentation slides ready?
Okay, let me share my file.
And at the same time, I can do the introduction for you. And
did you see my slide?
Not.
Yes, we do.
Yes.
Yeah, you can see my slide. Okay.
Yes. So around 18 minutes, I will try to give you a reminder, and only 2 minutes remaining. Is that okay?
That's okay.
Okay. So Dr. Fang is a professor and the head emeritus Department of Biometronics Engineering, National Taiwan University. He's a consultant to many companies and Farmers Association in Taiwan, Southeast Asia, Middle East, and China. He's also a project leader on automation, agricultural automation, controlled environment plan production systems, and aquaculture projects. He has co-authored and authored more than 130 articles, 113 technical papers, presented 250 papers at global workshops and conferences. He has co-authored 16 textbooks and translated 3 plant factory related books published in 2011 and 2012. He is also one of the international consultants of Japan Plant Factory Association and is also chief consultant of Chinese Plant Factory Association. So Dr. Fang received his PhD degree from Biological and Agricultural Engineering from Rutgers University. So for your information, at that time, our second speaker, Dr. Ting, was teaching there. In fact, Dr. Fang is the first Dr. Ting's PhD student. So on the other hand, my personal undergrad research is supervised by Professor Fang. So today is like academia, father, grandpa, and the son sequence. So you know how stressful I am right now. So let's welcome Dr. Fang.
Okay, thank you for the kind introduction. 3 generations. It's not easy. Okay, today's topic is introducing controlled environment agriculture. And on top, you can see 5 icons. These icons are created by ChatGPT and under my guidance. And you can see they are including many details. Okay, and there are many terms to describe what is controlled environment agriculture. For example, greenhouse for crop production, plant factory, vertical farm, urban agriculture, urban horticulture, indoor agriculture, horticulture, or city farm. And a lot of Korean researchers, they tend to prefer smart farm. And that is CEAG agriculture. And there is also CEAQ, that is aquaculture, and CEAP, that is aquaponics. So, and also from the right-hand side, you can see there is also indoor pig farm, sheep farm, milking cow farm, poultry farm, and fish farm, and especially insect farm. That's recently quite popular, especially in Southeast Asia. Okay. So, as I mentioned, control environment, agriculture, aquaculture, and aquaponics. From the right-hand side, you can see some modifications that I add is the small letters, small text, CEAG, AQ, and AP. Okay. And besides those small text, the graphic was created by ChatGPT. So totally there are 5. And this last one, I like it the most. It's because it includes the circulation concept, and it stands for the sharing of the feces from the fish or shrimp, and that can be the fertilizer for the plants to use. So in this kinds of system, we have a logo for promotion. The logo says that in such system, plants need no fertilizer. Human add in fertilizer. We don't need that. And for the aquaculture, the water, we don't need to replace them. So they can circulate for a long time. Okay. So that's what we describe such system. Okay. And the global trends right now is favor the development of CEA. Okay. Davidson once mentioned that in his famous novel, it says it was the best of times, it was the worst of time. Okay. And it is the worst of time right now because we are facing the following situations, such as overpopulation, urbanization. People like to live in the city, so they move from countryside to the city. And global warming, extreme weather, and resources always not enough, and population. So these kinds of poor condition lead us to such future. Okay, if we don't get some improvement, then this situation might happen. Okay, so I say that it is the worst of time. Not was, is, okay, is. And because of those situations have lightened consumer awareness, okay, such as food security, food safety, carbon footprint, and food mileage, and carbon neutral. And people like to have healthier and more nutritious food. So it is the driving force for the development of controlled environment agriculture. Okay, so and people start to ask. Okay, people start to ask, is there any plant production system capable of producing mass amount of high quality products in the shortest time, use the least amount of resource, and has the least amount of impact on environment? So people like to think, to ask, and the answer is yes. Okay, the answer is yes. Okay, CEA allows us to create a world where the food we need is made locally and sustainably everywhere in the world. Okay, so that's why I say it is the best of times for the development of CEA. And mostly we should thank the development of LED. Okay, LED. So it is possible in the future, even though the outdoor environment is so poor, we might have a building or several floors inside a building that can produce food to support human survival. Okay, okay. And with the advancement of LED, we can lighten up eco-friendly dreams. Okay. Okay. And here are other designed by ChatGPT. So just have a look. Okay. And of course, we should use renewable energy together. And CEA is not only for plants, but also agriculture, as I mentioned, and they can share the water together. So it's aquaponics again. So they are all within the CEA category. Okay. And that's from the outside. But inside the building, it's maybe in the near future, it will look like this. Okay. Okay. And how about food be grown in space? Vertical farming with artificial lighting could be how we grow food in space station or on Moon and on Mars. Okay. Now, from the beginning, traditionally, food was grown in open field using the sunlight, and the annual yield for the open field production normally is less than 3 kilo per square meter per year. Okay. The reason for the number is so small is because, for example, as shown in the pictures, it is lettuce, and it can be grown only during the winter season in Southeast Asia and also in Taiwan. Okay. And it may be only 3 to 4 months for the whole year. So the annual yield is quite small. And if you grow lettuce inside the greenhouse with the environmental control, for example, cooling and heating, and it is possible to grow all year round, then the yield can be much higher. And if you forget about the sunlight using LED, then with more layers, the annual production can be much higher. This is the plant factory in Taiwan. There are 14 layers. Okay? And this is another plant factory in Japan. There are 15 layers. And the annual yield is 150 times of open field production. Okay. And where are the places suitable to develop plant factory, or we call the vertical farm? The first choice is places with high population density and high income, because at present time, the cost is still high. Okay, the cost is still high. So the price cannot compete with the, for example, vegetable or fruit growth in the open field. So we need to have people with high income as our potential customers. Okay. But they are very concerned about the health and nutrition. Okay. And also locations that is too hot or too cold to grow vegetables, and with too little rain, and with shortage of fresh water and with cheap electricity fee and relied on imported food with little farmland, with lots of unused building, factories, basements. So these places that are very suitable to develop plant factory. Okay? And trends favor the development of controlled environment agriculture. The first one is the advancement of ABCDE and HILR. Okay. AI, big data, cloud computing, deep learning, edge computing, and HVAC. D means dehumidification. Okay. IoT, LEDs, and robotics. All of these, they are drops in price and increase in efficiency. And also more profitable crops and value-added crops are now becomes the main targets that plant factory people grow. Okay, and also products with beneficial phytochemicals. That is biopharmaceutical, food additive, or medicine. All of these are very popular. Okay. And the most profitable crop right now in CEA is marijuana. And this crop requires lots of energy to grow, but still they are profitable crop. Okay. But they are not allowed in Taiwan. We still consider that is some kinds of anyway, in Taiwan and in still some countries in Southeast Asia as well, we are not allowed to grow this. Southeast Asia, only Thailand is now okay to grow medicinal marijuana. Okay, and this is a friend of mine. They are growing medicinal marijuana in Thailand, and you can see they have several layers and with artificial light. Okay, and the main product is the flower because it contains the most concentrated CBD, which is the medicinal phytochemicals. Okay, and also some only use one floor, but some have several floors and fixed bench or movable bench. So you can find these kinds of facility not only growing vegetables but also growing marijuana. Okay. But marijuana is not the only profitable crops. Okay. This is what we grow in Taiwan and in China as well. This is ginseng. Okay, and ginseng people always consider eating root part, but we are eating the sprout. Okay, and they only grow for 1 month, then we can sell like this. Okay, and of course we are using LED. And compared to marijuana, the light intensity required is much less. Okay, as shown in this research, you can tell only 30 ppfd is necessary. It is okay. Okay, and for the marijuana, it requires at least 400. So it's more than 10 times. And the best is at least go to 1,000 ppfd. Okay, ppfd is the number of photons. The unit is micromole per square meter per second. Okay, and 30 versus at least 400. Okay, so you can tell a big difference. on the requirement of light intensity. And also, there is profitable crops such as strawberry. Okay? This is Oishi company, Japanese company, but they are now in New Jersey, New York, and they was also very popular. And the product sells very expensive. Okay. As you can tell, well, that was my role model. Okay. When I saw from the video, I saw their advertisement, and then I think, wow, they are so good. Just look at the products. But when I look into detail, I found that one box is 4.2 ounce. It's about 120 grams for 6. That is the biggest fruit they can grow. Okay, but 120 grams per box, and that is 6 fruits. So it's about 20 grams per fruit. Okay. So if the size is like this, then they are so-so. Okay, they are not so amazing. Okay. And this is a Chinese company in Hangzhou that me and Dr. Ting, we visit them. And actually, I was supervise this company for about 8 years from now. And this is the fruits that we can get. Okay, one box to 240 grams per box, and that is about 40 to 50 grams per fruit. Okay, and this one is the biggest, well, maybe not the biggest one, but it's the one that is pretty good size. Okay, so compared to these two companies, I'm quite confident that the strawberry production in China is much better than Oishi company. Okay, and we are setting up such facility in Taiwan right now. Okay, and also there are other other value-added crops for plant factory. For example, vegetable with special ingredient with functional plants and biopharmaceutical medicine. So the secondary metabolites are right now the focus of the plant factory company. Okay, because that market increased a lot. Okay, from the scale of millions to become billions. Okay, and conclusion: the best times for CEA development is now. Local for local is the core principle driving the development. And the advancement of LEDs, for example, perovskite LEDs are cheaper and easier to manufacture than traditional LED. So it's the main focus that we are expected. Okay? And value-added crops with great potential. So we really think CEA can play important role in urban agriculture. Thank you very much.
Yeah, you are so in time. Yeah, even not necessary to have my reminding.
Okay, so should I cancel the sharing, or you can do that for me?
Yes, but do you have time for some questions if people would like to ask questions?
Yes, yes.
Actually, I'll start to try to spark some other questions, but this is more of a comment. The LED was invented by Nick Hoynick at the University of Illinois, and I wonder if he had the vision of its importance to agriculture. And I think this is, when you talk about this technology, how has the LED helped drive down the cost of production?
Because the efficiency of LED is much higher than the the traditional, for example, traditional fluorescent lamp. So the electricity consumption is smaller, and the heat generated that need to be removed by air conditioning is also reduced a lot.
Thank you.
Yeah, I visited Nick in 1998 when I visited UIUC last time with other NTU colleagues. So I have a good chat with him. Originally, he gave me only 30 minutes, but we talked for 2 hours. And I talk about the application of LEDs. It's quite popular. But I just mentioned in Taiwan because at that time, Plant Factory is not so popular worldwide, not as popular as right now. That was 7 years ago. Yeah. Okay.
I think our local students can have a lot of chance to ask questions to Professor Fang. So I think to keep the time, we thank you again for Dr. Fang. And we try to move to the next speaker, Dr. Ting. So Dr. Fang, thank you. Thank you very much.
Thank you so much.
Okay. Thank you.
Thank you, Professor Fang. Can you stop sharing? Or?
And
So,
Casey, I think you can just take over sharing if you want.
Oh, really?
You can just-
Wow.
Yes.
A
I think you
new
start
feature.
sharing it.
Okay, let me see.
Here you go.
Can you see this?
Starting to come up. Yes, we can see it.
yeah,
Let's see.
Dr. Ting, I have some introduction for you.
Please.
Okay.
Thank you.
Our second speaker, Casey Ting, is the professor and the head emeritus Department of Agricultural and Biological Engineering, University of Illinois Urbana-Champaign. He was vice dean of International Campus Zhejiang University, 2017 to 2020. He has been leading research team to develop and implement the pioneering automation, cultural, environment-oriented systems analysis methodology, concurrent science, engineering technology, decision support platform, and intelligent-driven empowered agricultural systems framework to make food and agricultural systems work well, better, together, smarter, and wiser. He has delivered over 145 invited presentations in 17 countries. He was editor-in-chief for Computers and Electronics in Agriculture. He has participated in establishing international collaborative education, research, administrative programs between institutions in the United States, the countries in Asia, Europe, Middle East, South America, and Africa. He is fellow of ASME, fellow of ASABE. Dr. Ting received complete K-12 to undergraduate education in Taiwan. It's our honor to have such a distinguished alumnus. Our gratitude goes to him for continuous help and educating us for so many years. With highest respects, welcome, Dr. Ting.
Thank you very much, Professor Huang. That was quite an introduction. That doesn't sound like me anymore. But anyway, Professor Fang gave a very comprehensive introduction to the control environment agriculture. So his information is very practical and useful. So that will allow me to be more on the philosophical side. So indoor plant production, I'm going to limit my control environment agriculture to plant production because that's the major form of production in CEA, although there are many very value-added emerging production systems. So indoor plant production is arguable the highest tech form of agriculture that requires multidisciplinary expertise to be successful. So it also has a very high readiness level to take the advantage of intelligence and systems approach. So, so today we're going to discuss intelligent indoor plant production systems. There are three aspects in this discussion. One is, of course, the IPP itself, indoor plant production. Then we'll touch upon the intelligence and systems, actually systems of systems. So let's look at the evolution of IPP, indoor plant production. Of course, open field farming, then we start adding more and more capacity to the CEA to make it into protected cultivation, and then greenhouses. And then, for the lack of better terms, the advanced greenhouses will become control environment plant system, and then more a higher degree of closure, even AI and other things, automation added to that, they become vertical farming plant factory that you have already seen from Professor Fang's introduction. Then with vertical farm, there are other uses of plants. Professor Fang actually biopharmaceuticals and those kind of space agriculture, those kind of things. And with AI up and coming, then I started calling this whole autonomous IPP systems as a phytomation. So for many years, a lot of effort has been made to make agriculture and food systems work very well, better together, smarter and wiser. We have done a very good job to make the system work well and better. We have to continue to do a better job in making the system work together with systems approach and with intelligence in the form of smart and wise, knowledge-based and wisdom-based. So how do we do that? Actually, there's one more reason for indoor plant production to look at intelligence, because there are many factors. We have to define objectives and constraints of this kind of system. Plant culture, environmental factors, energy, labor, mechanization, we can always implement that into indoor farming, indoor plant production, and including machine intelligence. Therefore, automation is actually a functional integrator for indoor plant production. So what do we mean by automation? This is common sense now. It's basically the machine capabilities of information processing and physical work, including perception, reasoning, learning, communication, task planning, execution, and systems integration. So we can make machines do all these things for us. And one way to do this is a human supervised cyber physical system concept to achieve the goals of intelligence-driven and empowered agricultural systems. I call it ideas. So we have cyber platform, domain intelligence, and then physical form managed operation using machines, and then human being the supervisor of cyber and physical systems. So basically this data, information, knowledge, and wisdom, and then drive that into action. And then we have task planning and execution. So that's one form of implementing intelligence in controlled environment agriculture or indoor plant production. So a couple examples. Many years ago, 1986, or late 1980s and early 1990s, we started working on using robotics, machine vision, and some sensors to develop seedling plant transplanting systems. So actually at that time, Professor Wei Fan, using Visual Basic to hard code animation robotic work cell for us to study how to be the best layout for plant production, for transplanting operation. Nowadays that we move to a more higher forms of I just want to show you this strawberry harvesting robot. For the demonstration and for the interest of time, this speed is 2 times of the real speed. Okay, so it's still a little slow, but it's getting there. So it can identify harvestable mature fruit. Strawberry has to harvest at the mature stage because it does not improve maturity after harvest. So it can identify, it can skip the green ones and then move to the next one. And actually this platform can also serve as a monitoring I call it quasi IoT. So it can equip with many sensors running through this system once every so often to understand what's going on. So we don't have to put a lot of sensors side by side with the plants. So it can skip non-ready strawberry and to the next one. What I want to show you is the pictures on the right. This monitoring system, machine vision system, can identify different scenarios of harvestable fruit. Pretty soon you'll see there's a cluster of fruit that the robot is going to be harvesting. It can identify which one to harvest first. So the ones behind it will become available for harvest after this. You can see, so quite smart at this point already. It picks the ones that's ready and then makes the ones that not behind it to be even accessible. So that's the current stage of the intelligence driven and empowered agricultural system in terms of indoor plant systems. So let's go to the systems concept. Actually, the indoor plant production needs automation, culture, needs the consideration of automation and machine capabilities, and then culture, that's the growth and the development of the plants, and the environmental factors and control and delivery of environmental factors, and the system integration to make it work well. So this is a more detailed functional parts of a indoor plant production system, including automation part, including intelligence and operations research to be automated by machines, and then cultural part, the growing systems, the plant, how the microclimate and substrate nutrient delivery and those kind of things, and worrying of plant quality, and the hardware to support the plant, and also the environment side. Environment actually includes the indoor environment and the outdoor natural environment. We want to be environmentally friendly to the natural environment and also a productive environment indoor. So one thought is to how do we deliver this systems concept is through one suggested platform is called consent, concurrent science, engineering, and technology. So we have informatics, that's the collection, storage, retrieval of informations, like Internet of Things and big data. And then we need to process information using models and some analytical forms like machine learning. And the key is to bring conclusion to the decision support form, including analytics and cyber physical systems. And then, of course, we need to look at the strategic level, tactical level, and operational level of to achieve the system scope and objectives. So a couple examples, again, many years ago, late 1990s, we were working on the human exploration. Professor Fang mentioned this. To go to Mars to support human activity in space. So basically, you have the human component, and then you have the agriculture in space, and you have the kitchen in space, and you have to deal with waste management and resource recovery. It's a totally enclosed system. So how do we make it happen? So there was a comprehensive model developed to simulate from one day after another for the several hundred days in the space, how to support human lives. So this just shows this was done by Luis Rodriguez in our department, actually, professor now. This was his PhD dissertation. And then one very simple example is, one of the output is to study automation, how automation impacts crop production, because crew time in space is very valuable. We want them to do scientific work. We don't want them to just grow plants and do the kitchen to be able to survive in space. That's not the purpose. So we need to look at automation to save labors. So without automation, we are looking at the profiles over 200 days of operation. The person hours need, that's the crew time need over time. So with automation, the profile changes, but there are still spikes that requires labor. So this kind of study, this is only one of the examples of the output that can allow us to study the feasibility, workability, and how to optimize that system. Now, nowadays, the digital twins are emerging as a very feasible, in the manufacturing world, digital twins have already been implemented in indoor plant production systems, we can still look at crop management, environment yield. This is our A, C, E, and SIS level using cyber platform to couple with the physical platform, the digital twin. These are the twins, right? Twin brothers and sisters. So we have a cyberspace and physical space. They are closely coupled to help each other do a better job, also to grow based on their experiences. So to manage, control, and optimize plant factory. So that's up and coming. A few words about system and versus systems of systems. Normally, when we talk about a system like a car with engines and many other parts, that's a directed system, meaning that all the subsystems or components are guided, controlled by the central unit. So all the subsystems or components are working solely for this system. All your engines and all those things in your car are solely working for your car. But more and more, we feel that especially in agriculture and food system, that not all the subsystems will only work for you. So the tightness of central control start to loosen up. For example, it becomes acknowledged with a manager, sort of all the other, start calling them as constituent systems. They don't just work for you necessarily. And then it become looser and looser to become collaborative. They all agree to come to help. And the virtual systems, there's some invisible form of mechanism to make constituent system work together. So that's the concept of system versus the guided, directed system. Okay, with that, with the IPP, indoor plant production, and then the intelligence and systems concept, I think this is an opportunity to look at the circular bioeconomy system as applied to indoor plant production. The linear system of systems of, we started look quite often that when we talk about CEA, we only look at production side, facilities, but actually it's a whole value chain supporting the indoor plant production system of systems, because every step of the way is a constituent system itself. For example, the sales part, the supermarket, they don't just they don't just belong to you. They can serve others, other goods too. So, but in the linear system, we take from the natural resources and use them through the value chain and discard them. That's not very desirable. So we have to transform them into more circular system of systems, meaning that we have to intensify the resource use within each step, and also start to look at opportunity to share materials and resources discarded from each part through transportation distribution system, and then using the loop closing system called waste management resource recovery, many to many. It can come from any and then produce resource for other stages. So that's the concept. And actually the definition of circularity, there are five circularity principles actually presented by Ellen MacArthur Foundation and also ASABE, being refined, increase resource use efficiency, redesign, design out or eliminate waste and pollution at the design stage, and then reuse as much as possible, keep the products and materials in use. And even it's hard not to discard anything. Even if we have to discard anything beyond our scope of system, we need to make it no harm. Even better is to regenerate nature, help regenerate natural system like composting, as an example. And then if we don't bring this at the beginning, when we start to increase circularity, it will cost more money to enhance the circularity. But eventually we have to look for opportunities to reprofit, bring more profits to the practitioners. Otherwise, very few people will want to participate. I added one as resistant, because all these things have to work together. Not anything can work alone. So I call it 5+1 circularity principles. So we have to manage the system of systems. Okay, and then several years ago, about 2020, so this was published in Resource 2021, 8 of us got together to take a preliminary look at opportunities to increase circularity in different forms of indoor plant production, starting with greenhouse and then going to more advanced greenhouses like controlled environment plant systems, and then go to vertical farming and plant factory. So this is an example of how we collect information and chart them out. For example, in the basic greenhouses, composting may be able to collect waste and generate resources back to production, and using recyclable glazing materials and packaging materials can be recycled. Also, finding a way to decide what consumers want and then produce accordingly. So when we go to the next level, that's higher level, in addition to the greenhouse opportunities, we can also add more opportunity, because being a more high tech, we can start to improve social acceptance of the CEA produced products, and then we can maximize the nutrient use in plant growth, just for example. And then when we move to really high-tech vertical farm and plant factory systems, we start to open up a lot of opportunity. It's worthwhile to breed seeds, design crops for this kind of environment, start to do autonomous systems, increasing our use of intelligence, robotics, and automation, and then pay attention to market strategies. We can do designer. I started calling this kind of agriculture not production, call it manufacturing. It's called agricultural manufacturing instead of agricultural production anymore. Okay, so last year, we had 29 people gathered in Arizona, Biosphere 2, University of Arizona, Biosphere 2, to do a more thorough brainstorming sessions to come up with ideas. How do we advance the goals of circular control environment agricultural systems? So I am going to show you only one slide. Like I said, we have a proceeding of 181 pages of proceedings of information collected from that workshop, but I'm going to show you only one slide out of 181 pages. The high potential opportunities, this is very highly incomplete list. Measurements and standardization of inputs and outputs, very important to know whether we have actually increased the circularity. Automation is viewed as important. Design crops, I already mentioned. The workforce training, very important. That we were thinking about even creating a new profession called circularity officer for different aspect of business. And then AI, machine learning, already mentioned. Waste collection, logistics are very important, because when we talk about waste processing and resource recovery, we always concentrate on the processing itself. That's important, but in the end, the implementation will count on how good the logistics are. If you cannot collect waste in a very efficient way, the whole system will not work. So therefore, the quantification of food waste across the entire value chain is very important. And what is treatable, what is reusable, those kind of concepts. And then also, how do we know what we do actually help the natural environment? That's very important. Also, team building and collaboration across disciplines is very important. So my last slide is to show, if we want to do the system transformation at a system of system level, these are some suggested considerations in terms of convergence of multidisciplinary expertise and work. We have to train people to think divergently, but we have to come to the solution using convergence method. So we need a mission. Okay, without a mission, people don't come together. We have to define objectives, and we need to know trade-offs, because some of the things we do will have some sacrifices for other parts of this system of systems. constraints, physical, biological, chemical. There are many constraints that we have to realize, and we will involve multiple agents. Being a system of systems, agent-based approach thinking is very important. And of course, we need to be able to have mechanisms that help us measure, analyze, and then come up with actionable insights and take actions and do continuous improvement. So we have to know we need to involve multiple sectors, economic sectors, professional sectors, even governance sectors. And we have to know how we know if we make assignments to constituent systems, how do we know the components and subsystem constituent systems within our systems? How do we know that their actions actually will contribute to the overall mission goals? That kind of mechanism algorithm we need to have. And of course, we need to look at who would benefit, also who would not benefit. Very important. So we can convince people to participate. Also, inclusiveness and equity are also important. There are many more. So I think I managed to stay in time. Thank you very much, and 谢谢.
Thank you very much.
Thank you, Casey. There is a question from the Taiwan audience of what you think about digital twins and ag robotic systems. Is it necessary only for large-scale projects?
Economics, the current economics concern is that you need to have enough work for the digital twin and robots to contribute in order to be economically feasible. Okay, but it takes some creativity to, for example, when I study in the US, we always study large machinery, but when I go to Taiwan, they have small farms. So how do we transfer the kind of thinking and knowledge of designing large machines to be able to design localized machines for smaller farm? So the expertise, the capabilities are the same. The thinking and design process may have to be refined. Yeah.
Can you address, this is a question about the current linear production systems for CEA. On the current pathway, are there already elements of circularity taking place, or are CEA systems a producer of waste that have to be considered for large municipal facilities? Any insights from the production that's taking place around the world to know whether CEA is a natural circularity that's emerging?
Yes, CEA may be one of the most advanced form of agricultural production that has already been practicing circular bioeconomy. They are very watchful regarding use of resources already, and they are already thinking about, well, first of all, the water usage in plant factories is 95% efficient already. Okay, so they continue to circle, and they minimize the use of pesticide already. And also, there is an institute called Resource Innovation Institute. They have been working on circular bioeconomy for CEA for many years. They have many projects, and one of the representatives from that organization was a participant in our workshop. So CEA has already, but there are still some of the things, unfortunately, discarding is more profitable than reuse or recycling at this point. But those are the places to be improved. Yeah.
So there's another, thank you. There's another question from James Santiago, and the question is, the strawberry harvesting robot is amazing, but from the business perspective, how far along are we in getting a commercially available robot with a short return on investment time?
Well, there are already strawberry or many other type of robot, but strawberry robot alone, there are already commercially available robots being used in the indoor plant production systems, how beneficial in terms of economic return at this point, we don't know. But the particular robot system that I was showing is actually a company product out of a PhD dissertation. The person actually formed a company now to develop a commercial form. There's still much work to be done, but a company has been set up to manufacture, to develop that into a commercial product.
Thank you. Dr. Huang, I'll turn it back over to you. Would you like to have somebody introduce you?
I can introduce myself.
Okay. And finally, let's thank Dr. Ting for his excellent presentation as well as we move on.
Thank you.
Okay, so I'm the third speaker. Okay, so I'll talk about the CEA practice in NTU Smart Greenhouse. I'm Chen-Kang Huang, and I will introduce myself. Okay, so Chen-Kang Huang is my name, my Chinese character, and you can call me Bruce for your easier pronunciation. I also have my Korean character there since I need to have some interaction with them. I'm the third guy in this seminar. Get my BS degree from this department. Previous name is Agricultural Machinery Engineering, National Taiwan University. I then have my master degree in Mechanical Engineering, still the same campus. Then from year of 2000 to 2004, I got my PhD from Mechanical Engineering from University of California at Berkeley. My major is heat transfer. My two minors are precision manufacturing and microfabrications. So my research interests include the thermal science, boiling and condensation, immersion cooling, and the computational fluid dynamics. So I'm so happy to talk about this with you, but not today. And because from last August, I start to serve as the director for Center for Intelligent Agricultural Education and Research. We have a classroom, and we also have space for servers. And we have two groups in our center. Professor Chen is a research group leader. The CDA-CIA joint seminar cannot be held without her huge help. Last weekend, she also helped to prepare another two topics to collaborate with UIUC, and she will be the speaker in the webinar 4. And Dr. Ting is responsible for the courses and the workshops provided by the center. So next month, we are going to work with Taiwan Instrument Research Institute, 国研院医科中心, to have a workshop to introduce the spectrum application to agriculture. And he has been the speaker for the webinar 1. And the center also operates a smart greenhouse. We endeavor to make it precise, smart, intelligent, autonomous, self-sustained, and sustainable. We construct it as a platform for faculty in the college to demonstrate their research outcomes here. And currently, we hydroponically grow muskmelon in the greenhouse. So luckily, we have some comments with today's first speaker, Professor Davidson. So I will have a short video for you. Let me let you know our smart greenhouse more. So we have the evaporative cooling pad. Since Taiwan, the summer is very hot. So you can see the containers for hydroponics. And we have the pest monitoring system by Professor Carter Lin. And Professor Shifang Chen also have the muskmelon disease identification here. And then you can see some automation systems for the greenhouse. This is a nutrient tank. we have the solution quality monitor system. And they go on right-hand side, you can see a robotic arm. We will do the 3D phenotyping in the future. You see the huge fan to produce the negative pressure. And from you can see the tank for the nutrient heating and the chilling system. So those spatial markers are RUCO markers for UAV positioning. So this is hydroponic temperature monitoring systems. And actually, this video is from the POV of this autonomous mobile robot. The AGMR will be good to scout, patrol, and deliver liquid or powder to be closer to an autonomous greenhouse. Okay, so this is our agricultural AMR, and it equips with LiDAR to use the SLAM to construct the map and the position itself. It also performs A-star navigation algorithm to move in the greenhouse. The edge computing here, the edge computing is powered by our partner, the leading industry computer company in Taiwan, Davidson. And we plan to attach more modules, such as the microclimate station, to detect the abnormal situation or high temperature or high concentration of specific gases. Okay, so in fact, the environment parameters were measured, collected, analyzed, and subsequently processed, also by the system powered by Davidson. And currently, we have temperature, pH, dissolved oxygen, and the EC for nutrient solution. And we have temperature, relative humidity for indoor and air atmosphere. Okay, so we have sensors, and we have nodes, and we have gateways in the greenhouse. And using LoRa, we can transmit the data to a computer in the control room. And we have totally 24 temperature and the relative humidity for the indoor atmosphere. And at each location, like this one, we have a high location and a low location temperature measurement, and to construct the 3D temperature field. And then we also have four, this 1, 2, 3, 4 here, four hydroponic tanks will monitor and control. In the control room, an elegant graphic interface is for monitoring and the controls to display and store the results for future big data analysis. Yes, we have large nutrient tanks for stable nutrient quality of EC and pH. We also have the heat exchanger with hot or chilled water to regulate the nutrient temperature and to discover the role of the root temperature during the growth period. Okay, you can see the evaporative cooling pad and the fan, and that can generate negative pressure inside of the greenhouse. And so the hot air, outdoor air, passing through the pad become cool and humid, entering and cooling the greenhouse during the summer. Okay, so by using temperature sensors with the monitoring data dashboard, we can track temperature fluctuation in real time. Moreover, if the temperature exceeds a specific value, the negative fan and the cooling pad system in the greenhouse will automatically turn on, and preventing mass balance from being damaged by heat. Also, deep learning techniques with physics-informed neural network will be used with results from computational fluid dynamics to determine the best strategy for airspeed and window opening to achieve the best energy efficiency. Okay, so this is the temperature and the relative humidity contours. We have the overall greenhouse temperature and the relative humidity distribution are estimated using Gaussian process regression from data collected by 12 sensors. So from the temperature contour history, some hotspots, those red areas, we can see and can be found. So solutions are needed, this part. So solutions are needed to eliminate those hotspots to maintain the temperature uniformity of the greenhouse. Okay, we also use the data, the temperature data we have, and to discover the role of the growing degree days, GDD. So we aim to study how heat accumulation affects the growth of muskmelon. We select growing degree days, GDD, as our indicator. So briefly, GDD is a heat-based indicator measuring the effective temperature accumulation over time. So this is the integration of the temperature difference and with respect of the day, the time, and which helps to predict the plant development rates. So use GDD can predict the different developed stages in crops. So previously, there's mostly used for rice, and that has been well established for decades. So this figure demonstrates that GDD, along with the daily mean air temperature during the vegetative growth period for muskmelon. So we have the total 30 plants. There's the GDD and the height record, and we have the plate in a figure here. So the scattered diagram illustrates the relationship between the GDD and the muskmelon height. So by performing linear regression, we found R square coefficient of determination value of 0.92. So indicating a strong positive correlation between the growing degree day and the muskmelon height. And so this finding suggests that GDD is a very effective predictor for muskmelon growth. So in the future, we will discover more about this. Okay, so this is a fruit, and this is from another view of our greenhouse if a lot of muskmelon is matured inside. So current test, we grow in the greenhouse, we grow muskmelon 3 times annually. And the UAV, we have Professor Dr. Lin, he developed a UAV system, can fly in the greenhouse. And according to the video, and after processing the video, we can determine where the flowers are and where the fruits are, and to count the number of flowers and the number of the fruits, and even the position of those flowers and the fruits, and to have the better understanding the whole growth of the muskmelon. Okay, we have some future plans. So the first one is my team trying to develop a new version of the, we should say that's a smart weather station. So we not only the 2 parameters, temperature and relative humidity, we include the light intensity, this one, and also the air velocity and the CO2 and the oxygen concentration to be included. And so we expect that more comprehensive big data can be collected and for future analysis. And also the 6-parameter recorder will be placed in a precision orchid garden. So every 10 by 10 area of the garden will have one recorder, and any deceased plant in that area will be digitalized into images for future image processing and recognition. So the relationship between the environment parameters and the symptoms is expected to be found. This is our future plan 1. And our future plan 2 is another industry partner, Delta Electronics, 台达电子, provides a 222 nanometer UV lamp. That's a special design UV lamp. We all know that most of UVC lamp is a 254. This one is 222. It will be used in the agricultural field to test the disinfection capability. The test will be held in NTU Smart Greenhouse, as well as the Orchid Precision Greenhouse I just mentioned in the previous slides. Okay, so this is our future plan 3. So an international team will be formed to explore the sweet pepper, this one, Chen-Kang, and suffer from the thermal stress to find out the responses and the solutions. So with knowledge from professors from agronomy, 2个农艺系的老师 and 2 professors from horticulture 园艺系, and the Wageningen University, the one in the Dutchland, and Advantech, our industry partner, and the Taoyuan District Agricultural Research and Extension Station, Taoyuan区农业改良场, and the CIA will work together for this project. So this is a kind of a subsequent activity after MOU signed last April. We have the MOU, college level MOU with the Plant Science Group, Wageningen University, and the research last year. And the CIA is also funded by the Ministry of Education Taiwan, and to collaborate with Texas A&M University. So we expect to have more communication with this AgriLife Research and the Extension Center at Dallas. So we will have 1 graduate student sending to them to work with them, and in early of the September. This is Professor Zaki. He visited us last November. So we also have a good interaction with Hokkaido University. So just last year and this year, we have a lot of the mutual visits. So this is a little workshop symposium, just will be held next week, next Wednesday. So last one, we also have the center level MOU with a global smart farm education research center, Seoul National University. And this is a workshop just occurred last month, February. Okay, so finally, this is a UIUC. So last year, our group leader, Professor Shi Chen, visited UIUC. I think that's last March. And we then had a chance to meet each other at Jeju Island. And Professor Reed visited NTU last October. So now we have the webinar series today, and the next 2 will be April and end of April. So now we have the webinar series. Sincerely, we expect to have more interaction with UIUC, solve some problems together, and have more impacts. Okay, so this is my last slide. So I would, my appreciation goes to my lab, my students, and many thanks for your support and hard working. Happy to work with you. Okay, so thank you very much. This is my last slide of today's talk, and it will be happy to accept any comments or answer questions. If time is limited, not enough, so please email me, including all questions about all professors today. You can send me email, and I try to reply quickly. I still remember Dr. Ting instructed us to be responsible and responsive professors. Thank you.
Thank you for your presentation, Dr. Huang. I don't see any questions in the chat, but I'll start by asking question about as we form CEA facilities, are there architectures that are emerging? So, for example, in precision agriculture, there are farm management information systems. So are there standardization of CEA management facilities that are emerging? And what's the degree of, I mean, CEA feels like it has a significant digital transformation component. Can you say a little bit about the maturity of the digital transformation in controlled environment agriculture?
Yeah, thank you very much for your best question. I think the standardization is a huge challenge for CEA and for a lot of the smart agricultural, precision agricultural in this industry, because of the sometimes because of the cost, sometimes because of the market, and it's quite hard for people to start the standardization. Like recently, we try to have now we have the smart greenhouse, but in the future, we try to have a smart ranch in the Taipei campus here in NTU. And we found out that a lot of the ranches in Taiwan, they already have their information systems, but they don't have the same interface, and they don't have the same data structure. The structure is different. So it's so hard for them to share information together and to accumulate their knowledge. So that I think you are asking a very difficult part, and a lot of effort should be pay more attention on this part.
Thank you. I have a question from the Taiwan audience. Can controlled environment agriculture replace traditional farming methods in Taiwan, or will it form a collaborative relationship with traditional agricultural methods?
Oh, okay. This is a very good question, and I think even Dr. Fang got a lot of questions about this. I think if just in Taiwan, the CEA production is never wants to compete with traditional ways, because I think the environment, the outdoor environment in Taiwan is still good enough to grow healthy and productive agricultural product. But we still try to develop CEA because we worry about the climate change. We worry about that if somewhere in the planet we suffer from out of the rain, out of the clean soil. So at that time, maybe CEA will be very useful. But on the other hand, CEA is very useful to grow some significant and pricey product like the ginseng and some medical plant mentioned by Professor Fang. And I also consider that even wasabi is very important and very useful and helpful to grow in CEA environment in Taiwan. I hope I answered the question.
Yes, thank you. I think this is actually, we all tend to be engineers and scientists in these topics, but I think this kind of touches a little bit on the social economic applications of CEA and how the role of small to medium enterprises are involved in providing some forms of food production to cities, perhaps not at large scales like CEA can produce. And I guess my question is, this is a little bit like in circular bioeconomy. It's not just a science and technical system of systems, but we need to connect to social scientists and understand how to move, deal with the cultural aspects of agriculture and move the producers into opportunities into the space. And I don't know if you have any comments about that in general, but it feels like it has a cultural element that's really pretty important for us to understand.
Yeah, I totally agree with you that I think a lot of the consumers in Taiwan, they still consider that vegetables from CEA systems are not as not as strong as those grown under sunshine. And so I think the consumer affects the market, affects the price. And on the other hand, even our government try to promote the smart agriculture. But on the other hand, the whole infrastructure and the people, the farmer, they are still a little bit afraid of using those technologies and the new technologies. So I totally agree with you that we have something we need to do to shorten the distance between the different levels, and that will help the promotion of the smart agriculture and also digital agriculture and the CEA.
And I can see there's some comments in the chat, but perhaps your father and grandfather in research would also like to make some comments. Dr. Ting or Dr. Fang? If you do, please come up.
I already mentioned in the chat.
Yes.
So Professor Fang maybe can read that.
Yes, I can read it as well. The question about will it form collaborative relationships with traditional agriculture, you said yes, CEA can work together with traditional agriculture. It just provides alternatives to produce plants. And then also you said, but it is also a driving force to traditional agriculture to be improved, to be more environmentally concerned and more environmentally friendly.
Yeah, anyway, thanks for my academic father and academic grandfather to join the seminar today. Thank you very much. Thanks for anything, your education.
I do not have much to add, but as I mentioned, it's a high-tech form of agriculture, and it's ready to implement a lot of technologies that are benefiting commercial business and manufacturing. So through that channel, it will become an example of how to use high-tech in agriculture. So it's going to elevate the acceptance rate of technology into agriculture as an entrance point. For example, circular bioeconomy systems, CEA has been doing that and is ready to do more. So it can become a model system for food and agriculture, not only in the future, but to advance technology adaptation in agriculture.
Thank you all for your comments. And before we move to Paul Davidson, I would like to ask, could you briefly say something about, it seems like this is an area where there's an opportunity for creating new jobs for the future that are be able to employ people in urban areas that are closer to the production of food. Do you have programs? I mean, those jobs can't be with PhD students only, or even undergraduates. Is there some thinking about developing jobs for people that are professionals that would be involved in controlled environment agriculture in the various locations you've worked in? You see this happening in Taiwan or in China or in other Japan or other geographies. Do they develop a workforce that has new skills and new jobs for CEA?
Well, in the U.S., the USDA has been funding multi-state, multi-regional projects to look into the workforce development for CEA, and many other, some of our sister universities are collaborators in designing curriculum and courses to be taught online or in person. So the effort has been made in that regard in the U.S., yes.
Okay, thank you. Let's go on, Professor Huang. You can make the next introduction.
Yeah, okay, so Professor Davidson, you can consider to have your presentation slides ready, and I start my sharing. So Dr. Davidson improves and maintains the surface water system by reducing the transport nutrient, passenger, and pesticide from agricultural system to waterways. We work with farmers and other stakeholders to develop solutions that protect our quality of our water resources while maintaining the efficiency farming operations. I have to say that in Taiwan, eutrophication occurs in some of our dams due to overuse of fertilizer. I think this is also a very important topics we should pay attention on that. So let's welcome Dr. Davidson.
Yeah, thank you. Are you able to see my slides okay?
Yeah, it's okay.
Okay. Well, yeah, good evening and good morning to those of you in Taiwan. So I'm going to talk about using recycled wastewater and then how we might be able to utilize that in CEA systems. And so I've got a few photos here. I want to acknowledge all the people in my group who are also making this work happen. So the picture in the middle is some of my undergrad students as well as my grad students who are working on this wastewater treatment project. And then I've also got some photos of some current students. Liam here is in the audience on Zoom. And then we have a picture on the left here with our aquaponics system in one of our greenhouses on campus with a couple of our former students. I wanted to start by mentioning that I have visited NTU, but it's been many years ago. So June of 2008, I was a graduate student and I traveled to Taiwan to NTU with my advisor, my graduate advisor, Dr. Prasanta Kalita here. And we taught a 2-week module on non-point source pollution. So actually talking about some of the eutrophication nutrient runoff aspects. It was Professor Huang, I believe, there is the class that we were visiting. And then, of course, we got to enjoy some of the sites and enjoyed a night market. And so I'm looking forward to my next visit in the future. It was a wonderful time, a beautiful country. And I also wanted to mention quickly before I jump into the topic for this presentation, I also do some work on low impact development, specifically permeable pavements. And one of the pavements that we are researching is the JW Eco Technology, which is a permeable pavement that was invented by an engineer from Taiwan. So here in the middle of this photo, some of you may know him or recognize J.W. Chen, who invented the pavement. He visited our site. He helped us install the pavement. He's visited us since then as well. And then we have Dr. Luming Chen here, who's a visiting research scientist at U of I, oversees this permeable pavement project. And Luming, I believe, is also on the Zoom call. So I wanted to mention that that there's another connection between U of I and Taiwan. So the topic of this presentation is on this idea of taking a biomass. And so in this picture, the biomass is food waste, but it could also be something like swine manure, pig manure. Putting that wet biomass into a hydrothermal liquefaction process, we call it HTL, and the primary goal is to produce biocrude oil. So if you attended the webinar a week ago, you heard from Dr. Yanhui Zhang from the University of Illinois, and he's interested in taking that biocrude oil, upgrading it to transportation biofuels. The interest for my group, though, is looking at one of these byproducts. So there's a gas product that comes out of this process, a solid residue, and one of my colleagues at University of Illinois in civil engineering is taking that solid residue and making a biobinder for asphalt pavement. But the interest of my group is taking the wastewater. And so this is kind of that liquid byproduct that's left over after the biocrude oil is produced. We call it HTLAP, so that's hydrothermal liquefaction aqueous phase. So that's the wastewater. And we know, depending on the feedstock, so depending on what is put into the HTL process, there could be potentially toxic compounds. These could include heavy metals, which we have seen when swine manure is the feedstock. With food waste, we have not seen heavy metals yet, and we don't expect to just because of the source of feedstock. But there can also be things like organic nitrogen and aromatic compounds. So there's some of these things that we want to make sure that we are able to remove from the wastewater. But on the bright side, we also know that this wastewater is nutrient rich. So it has high concentrations of nitrogen and phosphorus, which are the primary nutrients that we want in order to use this treated wastewater to grow plants in a hydroponic system. So this is kind of the overall picture of what we're trying to accomplish. So like I said, we know it's nutrient rich. We also know from past research that it has no pathogens. So the HTL process is a very high temperature, high pressure process, and it is essentially free of microbial activity when the wastewater comes out. So we don't have to be too concerned about that from a food safety standpoint. We still have to consider there are stages after the HTL process where pathogens could be introduced. But when the wastewater comes out, we're pretty confident that there's no pathogens in it at that point. And then we want to use this treated wastewater. We want to get more value, the valorization, by growing high value plants. So both edible plants, and we're also looking at some ornamental plants. We know that most of the nitrogen is in organic forms, and plants cannot access those organic nitrogen compounds. And so we need to find a way. So part of our treatment process needs to include ways to convert the organic nitrogen into either ammonia, ammonium, or nitrate. And so that's our big task. This picture is a laboratory hydroponic system that was used by one of my former master students. And so this is him, Samuel Jess. He graduated several years ago. He's now pursuing his PhD at the University of Arizona. But this was the basis of his master's research, and he grew lettuce using a few different wastewaters that had undergone different treatments. So this was wastewater from swine manure. So swine manure was the feedstock. And then the HTLAP that came out was diluted with just tap water in this case to a 2.5% solution. And we did some very basic treatments, filtration. So we use sand filtration, we use carbon filtration, and then we also tried using sand filtration and then supplemented it with hydroponic fertilizer. So we supplemented it to get it up to the same nitrogen value that you would expect in a commercial operation. So what we found, so treatment one here is our positive control. That's where we use the recommended fertilizer amounts. And then treatments 2 through 5 are variations of the HTLAP wastewater. Treatment 2, for example, was just sand filtration. And then treatment 5 was the sand filtration with the supplementation of hydroponic fertilizer. So you can see that we were able to grow lettuce in all of these situations. It didn't grow as well. And even when we did supplement it with hydroponic fertilizer, we still didn't quite achieve the same yield as we did with the positive control. We then analyzed the lettuce tissue to see if any heavy metals were getting into the edible part of the plant. We looked at cadmium and mercury, did not find any detections, very, very low detections of those. For lead, we did see some detections in the lettuce, but the circle is the maximum level that is recommended by the USDA. And so in all cases, the lead concentration was below that maximum. But then for arsenic, we did see in a few cases that the levels in the lettuce did slightly exceed what was recommended. So we know that that is something to consider in future experiments that utilize a wastewater that comes from swine manure. So some of the highlights or the takeaways from Samuel's work. First off, we can grow the lettuce. We can grow lettuce using the HTLAP. So going in, we weren't sure if that was possible, but we can. So that was a good first step. However, the yield or the biomass is lower anytime that HTLAP is used, indicating possibly a nutrient deficiency because the nitrogen is tied up in organic forms. However, we also have this instance where in treatment 5, when HTLAP is supplemented with hydroponic fertilizers, the yield still doesn't reach that of the positive control. And so there's this possibility that there's some inhibitory, potentially toxic compound that's preventing it from reaching that maximum growth. So we know we still need to do more treatment. The sand filtration and carbon filtration was not enough by itself. So how else can we treat the wastewater to increase the nitrogen that's available for plants? So one method that we have looked at is mycoremediation. So this is the use of a fungus. We apply that to the wastewater, we let it incubate for a period of time, and we see if it is able to then break down some of those organic compounds. The fungus that we selected was Trametes versicolor. In the literature, it's been used successfully for treatment in some other types of wastewater. And so we tried this one. And our questions, research questions, were it increase the ammonium nitrogen concentrations? Can it increase nitrate concentrations? And can it reduce the COD, or the chemical oxygen demand, kind of that organic reservoir that's in the wastewater? And if so, then can we determine the optimal cultivation period? So how long would this fungus need to be in the wastewater to be effective? So one of my past students, Victoria, and she published these findings last year, if you want to read more into it, we found that both nitrate and ammonia increased after day 3. The nitrate concentration peaked on day 3, and it went from a starting amount of 1.87 ppm or milligrams per liter up to 30.8. So that's a 17 times increase. That's a very significant increase for this wastewater. And there's the point where it kind of reaches that max on day 3. At that point, we see that the nitrate starts to go down, and then it goes down quickly, whereas the ammonia actually goes up. Whereas, again, we're interested in increasing nitrate. That's the preferred nitrogen form for plant uptake. And so we're trying to figure out what's happening there. So our hypothesis is that nitrate was consumed by the fungus in the absence of any other preferred source. So that's kind of a turning point where nitrate is just the most easily consumed form of nitrogen. And so that's what the fungus goes after. From this experiment, we determined that our optimal cultivation time was that 3-day time point. But we also wanted to know, can we do better? So can we further increase the nitrate, the plant available form, concentration by adding an additional treatment step? And in this case, it would be bacterial nitrification. And so that was our next step. We did an experiment where we applied the fungus, Trametes versicolor, by itself. Other treatments, we applied the bacteria plus Trametes, which is this one. And then we tried some other combinations of incubation time. What if we put the bacteria in after, so several days after the fungus? And this work is also published. Carla Lopez published that last year if you want to read more on it. But a couple of things I'll point out is this treatment here, the TV-5-HTLAP, is the treatment where we inoculated the wastewater with just the fungus for 72 hours. And we saw a very nice increase in nitrate from 2.07 up to 16.04. And then the next one, where we added the nitrifying bacteria, we saw an additional increase all the way up to 34.76. So more than double simply by adding the nitrifying bacteria. So that was a very important finding for us. The other thing I'll point out is that here is just the wastewater. And then this last treatment over here on the far right is when only the nitrifying bacteria were added to the wastewater. So no fungal treatment. And there's no statistical difference. So nothing really happened when only the bacteria were added. And so some of our takeaways from this are that the highest nitrate production is when you use both the fungus, the Trametes versicolor, in addition to the nitrifying bacteria. And when you add those at the same time, we saw that the nitrate concentration more than doubled. And then we also saw that the fungal treatment is necessary, we believe, because it breaks down those organic nitrogen compounds. So the microremediation is one treatment option, but we're also pursuing other options to see, what else is out there and what might work best. And so the next treatment option is electrolysis. This is where you apply current across two electrodes, a cathode and an anode. For us, the data I'm going to show, we used a boron-doped diamond electrode and stainless steel. You can apply different currents. You can apply that current for different lengths of time. And so I'm going to show a few results from that. And this work is being done by one of my PhD students, Camilla, and she'll be defending her PhD 2 weeks from tomorrow. So we'll hopefully have more results to share in the near future. But here's a few preliminary findings. This picture is a picture of her setup in the laboratory. It is very small scale. So you notice it's a very small volume that we're treating at this point. We're trying to see if it works. We're trying to kind of optimize the process. And I'll mention it later, but one of the challenges will be scaling this up. Can we produce enough treated wastewater using this process to grow crops in a hydroponic system? We've tried 3 different current densities. So in this top figure, looking at the removal of COD, chemical oxygen demand. And so you can see when you apply different currents, we do get different removals of COD over time. And then we also have done an experiment where we look at using a diluted wastewater. So in this top graph, it was 100% wastewater, no dilution, which is nice because you're able to treat the raw wastewater. But we wanted to see in this bottom graph, what if we dilute it in half? What if we have only a 25% solution? And so we saw a difference in nitrate content. Over time, over the current, You could see the 25% here shows that we might be able to get a higher nitrate content simply by diluting the wastewater, which would be something that we could easily do if that was something that would make the treatment more effective. Some highlights from this, and so one of the important things with this is that electrolysis does allow us to treat the raw 100% wastewater. With the fungal treatment, the mycoremediation, we were using 5% solution, so a very diluted solution of wastewater. But here, we're able to treat the raw. And so that's an important aspect. We saw an increased production of nitrate and ammonia throughout our different experiments. And then future studies, which Camilla is wrapping up now, will explore the impact of constant recirculation of the wastewater to increase the contact time with those electrodes, as well as adding a bacterial nitrification step, sort of like we did with the mycoremediation. So we saw a very big improvement with the fungal treatment. And so we're wanting to see, can we see a similar effect if we add on nitrification after electrolysis? So here's a picture of Liam. This is one of our laboratory hydroponic systems. I think here he's setting up one of his microgreen experiments. And this is just one graph. He's collected a lot of data at this point. But in this case, he was looking at lettuce microgreen production using two different wastewaters. So the blue bar is Kraft salad dressing. So it's a salad dressing feedstock that goes into the HTL process. The orange bar is Harvest Market food waste. So this is from a local grocery store, and it's a combination of different food waste. The negative control is just deionized water, and the positive control would be deionized water with your standard hydroponic fertilizers. And so you can see a 2% wastewater all the way up to 8%. As the concentration increases, as you get a higher concentration of wastewater, the lettuce microgreen yield or the biomass decreased. But we did see at 2%, we could almost achieve a similar yield as what you would expect with your positive control. And so some initial takeaways from this, and Liam is still actively pursuing some of this work. But again, we can grow crops using this wastewater. We can't grow it as well yet as you can with hydroponic fertilizers, but we are able to grow it. There's a combination of inhibitory compounds and low plant available nitrogen that leads to those lower yields. Liam found that diluted HTLAP up to 8% has no effect on lettuce seed germination. And that's part of a paper he published last year, if you want to read more into that. And then we have ongoing experiments that will further explore both edible plants as well as ornamental. So if you think about the cases where heavy metals might be accumulating in the plant tissue, you wouldn't want that if the crop was edible. But if it's an ornamental crop, that might not be as much of a concern, so long as the plant is being disposed of properly once it's past its useful life cycle. So what's next? So within my research group on this wastewater treatment project, we want to figure out how we can increase the efficiency and effectiveness of the treatment. So we are starting to learn what treatments are effective, but we're doing it at a benchtop scale. And in order for us to have enough volume to do our full-scale hydroponic experiments, we need to increase the production of treated wastewater. So that's a challenge and something we're actively working on. We're going to continue using the treated wastewater to grow both edible and ornamental crops hydroponically. We have a couple of laboratory hydroponic systems, and And so we're trying to get those dialed in, make sure that all the conditions are appropriate for the experiments that we're pursuing. And then, of course, explore the feasibility of scaling up some of these wastewater treatment methods. So electrolysis is somewhat energy intensive, and so we need to make sure that we can do that in a way that is also cost effective. That's all I've got, so I'm happy to take some questions.
While you've been talking, there's been some questions in the chat, and I think I'll just summarize them in case the audience did not get to see them in Taiwan. Dr. Santiago has asked, were pH and EC the same in all of the treatments earlier, your 5 treatments that you showed? And Liam has answered him that the pH was not controlled or monitored in Samuel's study, but Liam does plan to monitor pH and EC in his upcoming experiments. The dilution ratio, Liam says, makes the solution more neutral compared to the raw HTL AP, which is around 3.5 to 5. And they're going to get together with each other. And we formed a relationship here between, we found another person that's interested in controlled environment agriculture as a result of this. Thank you. Thank you very much for that. And
that's perfect, yeah.
And then Dr. Fang made some comments that pH needs to be controlled. And you need to convert, you need H+ to convert NH3 into NH4+, then bacteria to aid in the conversion to NO2 and then NO3. His lab has used organic fertilizer for hydroponic production. It normally takes 2 to 3 weeks to allow NH3 to convert to NO3 at around a concentration of 250 ppm. And then now some new questions, Paul. Questions from the NTU audience. What is the transferring process efficiency of biocrude oil?
Well, that would be more Dr. Zong's area. So I don't know the details of the biocrude oil production. I could certainly
Yeah, we
ask him.
can definitely, and in fact, that was, I believe, a comment that was in the lectures from last week. So you might go back and look at the audio or video recordings of last week or the PowerPoints, but we can actually ask Dr. Zahn to help provide that answer. And then the second question is, what advanced treatment technologies can be employed to ensure optimal plant uptake, food safety, and long-term system sustainability?
Yeah, that's a good question. So several aspects there. I think, we're working to try to figure out what, treatment technology might be best or might help us get the nitrogen into the nitrate form, which will then help plant uptake. So that I think is to be determined. Food safety is a really interesting component of this. So I have a background in water quality, and so I've worked with pathogens quite a bit in water. And so that is something I would certainly be interested in looking at. But we also know that the wastewater, when it comes out of the HTL process, is free of pathogens. So it hasn't been a top priority. We've really focused more on things like heavy metals from a food safety standpoint. We are now starting to think about food quality, I guess you might say, or the nutritional aspect of that. That's something that Liam and I have been talking about a lot lately. And so that will be yet to come. And the long-term system sustainability. So we do have a project where we're collaborating with somebody from Rutgers, actually. And she is working on the techno-economic analysis, the TEA. And so we will have some initial information about the feasibility and kind of that future sustainability of the process, but we're not quite there yet. So maybe give us another year or two.
And I think Liam basically concurs. So, so thank you for that. Any other questions?
So regarding the transferring process efficiency of biocrude oil, Sabrina Summers is in the audience. I don't want to put pressure on her, but she should be able to sort of answer that question, I hope.
Yeah, I can answer. For our HTL of food waste, our biocrude yield is typically 50 to 60% for the two feedstocks that Professor Davidson just mentioned. And then the corresponding carbon and energy efficiency is about 60 to 70%.
Thank you very much, Sabrina.
Okay, we have, if there are no other questions, this has been a fantastic webinar on controlled environment agriculture. I'd like to thank each of our speakers, Dr. Wei Fang, Dr. Casey Ting, Dr. Chen-Kang Huang, and Dr. Paul Davidson for their contributions to this. And if you have any questions, I'm sure all of our speakers will welcome an email to address these issues further. Thank you to all the speakers.